In order to implement other light sources, we just have to modify the fragment shader. Everything is provided directly from the main application, so we don't have to deal with anything else but the fragment shader, since we are computing everything using Pong. We just duplicate this line, and we want to have light position as another uniform path. And of course, in order to select which kind of light we are using, we can use just a simple integer, and we call it light type. Okay. So we added the position so that we can implement a point light, and an integer that enables us to select a different light without having to recompile the shader. So there was a part, and light direction, that we have to ram out. This is because in this way we just computed light direction for a directional light, but we want to generalize the process as much as possible. Eye direction doesn't change because it is tied to the space selected and not the kind of illumination, as well as the normalization of the normals. So bring them closer together. Instead of having just this, we want to use a vector 4. This is just one of the many ways in which you can implement something like this. This is a general approach. In your exercises at the exam, you might be asked just to implement one kind of light, not all of them. So now we see something which is general, which produce all the 4 kinds of lights as wanted. But you don't need to replicate this approach at your exam. Let's call it light model. Lm is going to be a vector for storing the color of light, not only not the color, the direction and other parameters of light. And we call for doing this light model. Light model is a function that we will create inside the shader, just to see, for a didactical purpose, the fact that inside the shader you can have function. And we want to pass to this light model function first light type, in order to specify which kind of light we want to, and then fs position, because we need to correctly compute the bouncing of light over the surface, the position of the surface. Then we are going to use as nLight direction, so in order not to change too much of the subsequent part of the shader, as the direction, we just collect the first 3 values, RGB for example, that can be misleading, just the first 3 values out of this vector 4 vector. Instead, we are going to have a float that we call light dim. Is not a light dim is going to be the last ln.a, the last value. The dim will be the dimming of the light, will be the dimming of light. So we need to apply this light dim to the to a scale factor for the diffuse as well as for the specular. Okay. Why this? Before all the space was illuminated by some light. In this case, since if we have a point light with decay, so it will illuminate up to a point, then start to decay up to fading to black, and also because we have spotlights which illuminate only a corner of the scene, we have to reduce the influence of light in a controlled way. Okay, we now have to implement the function for light model, and it will be a vector 4. In this way we can return more than a value out of the function light model, which is going to have light type LT and a vector 3 for position that we can call pos. Okay. Now we still have to normalize the light direction, so we create a vector 3 called n light dir, which is also going to be our output, the direction of light that we need, and two different other values which are they are just float. A float, which is the dimming of light, LDIM for example, and light cone when we have a light cone. We set light dim to 1, so everything is for now under light, but we will modify as the different light sources become implemented. So if LT light type is equal, for example, to 1, we decide that this is going to be the directional light. Our output value is going to be to minus normalize light direction, as we did previously. And again, light dim can be 1, because everything is exactly as it was, everything is under perfect light, so no dimming, no diminution of light, and just a direction. Okay. Else, if instead this is going to be, let's say, 2, we now want to implement a point light. Okay, and in this case, this value here is now a position, but doesn't matter because it's still a vector 3, and it is normalized difference between light position and the surface, so pos, I suppose. Is that right? Yeah. Okay. Since for a directional light we already have a direction, we just have to normalize it. Instead, if we want the light direction when we have a position in the space, we have to subtract it to the position over the surface. And in this case there is no decay, so we can let LDIM as it is. Now let's see a point light with decay. So LT equal to 3. Okay, in this case, of course, this is more or less the same, but we want to do something a little bit different. First of all, we have to define a length, so let's use the length, light length, to see how far we are from the origin, and we use for this simply the function which is called length. Light position minus pos. Okay. Then our n light is going to normalize light position minus pos, but so it doesn't change really. What doesn't change instead is let's say 160 as a given dimension for light with a linear decay. So okay, in this case we are computing both the direction from the surface to the point light, but also the distance between the surface and the point of light, deciding that the illumination power of our point light is going to decay using this formula as long as we go, is a quadratic basically, as long as we go farther away from the light source. The last and more complex case is the implementation of the spotlight. And it's more complex because we have to take care of three different situations. When the object or the point in the space is inside the light cone, the condition when the point is completely outside the lightning cone, and the position when the point is in the drop-off zone. Spotlight are not just a cone, there is a fall-off rate which expands the boundaries, creating a fading effect along the border. So it depends where our point falls, in which category our point falls. And so the direction is going to be the same as before. So we just normalize light position minus pos. But now we have to compute an angle. I don't know if I have some slide to improve the visualization of this, but I don't think so. We should probably make so basically we have to see, given the direction, how far is the angle between the source and the point, considering a vector which is the light direction. Let's create this cone. We have defined it as a vector 3 before, as the dot product. Minus is to correct the direction between the normalized light we just defined and the light direction, which is here, for example, but it's better to normalize it. And then we select with an if the different cases. Okay, in L cone we just have the angles between the direction of light and the point over the surface. So if L cone, let's say less than 0.5, sorry, just LD is 0. Okay, in this case the point is completely outside the fall-off rate. Instead, if is more than 7, 0.7, the object is going to be in full light, so LD is equal to 1 as it was. Else we have to compute something, because it is in the fall-off rate, and so we say that something like I think I will make a slide to explain exactly why those lines. Now, not having the possibility to draw anything, I don't want to um, let it just like this, because I think maybe it's hard to understand. So I will put a slide to clarify this point. We are missing a link on line 41. Thanks. Else. Is it right to use this condition on line 56? Shouldn't be as if as A equals to 4. I think that the results will be between 0 and 1. If we skip the first condition, so it's not less than 0.5, it is not up this other part, it remains only in this. Oh, sorry. 4. Sorry. Is this right? Yes, you were right. Oh, sorry. So now we have to return a vector 4 created in flight that use nlight direction as the first 3 values and ldim as the last one. In this way, we can have a multiple return from a single function. We don't have to create 2 functions. And then it is possible just to extract the values that we want in this way. Let's see how many mistakes I made decoding. Okay. Okay, not that many. So, point light. We have a point light somewhere. You can imagine. Oh, sorry. Okay, let's move in a better position. And then let's move the light itself. As you can see, there is a point into the space which emit lights, and if I move it around, I can see how it varies in influence. Probably looking at the highly illuminated zones, you can guess where this light source is. Okay, if I switch to point with the decay, you will see that there are parts in which the influence is very high. Probably I should, okay, move it a little bit. Oh, there's something strange, probably, okay. And there is a small, but clearly identifiable zone in which the border is less defined. Yes, it fades toward the black. Points really outside becomes darker. Okay. Spotlight instead, oops, project the cone. Okay. Of course, there is no shadowing, so each object is illuminated as no other object stands between. That's why you can see clearly this portion of the cube without the influence of the plane, for example. Also in this case we can move the cone and also rotate it. Both things can be done in this case. We rotate just the cone. Okay, so this example basically shows you in just one function how to implement different kind of lights. Okay, now we want to change, instead of having a Phong Blin reflection method, we like to have a Phong. How to do this? Instead of an H vector now we want to have a reffle vector 3 reflection vector reflection, okay, which calls the reflect function, which does exactly that, and following the formula we need enlight direction and the normal to the surface, no approximation but the correct reflection vector. Then we have to change the specular component. Now always a clamp, always a dot, but not n normal. We need to change those two parameters and put reflection and the eye position, normalized eye direction. Okay. Let's see if it is correct. Okay. Which the results, given what we have, I think is not so easily seen, but there is a difference. It's another formula. Okay. Now, to conclude this thing, let's do. Yes. It's strange. I think there's a mistake somewhere in the code, but I think that if I'm lucky, in a couple of minutes I'll find out. If I'm not lucky, I can spend the rest of the lesson trying to guess where the mistake is. In the example I provide you, this is correct, and you don't have that strange things. It can be something optic. You raised the question, now I feel compelled to find why it appears. So let's not have a look at that, so I don't spend the rest of the lesson trying to, because what I want to end the lesson with is how to implement the other two kinds, the Gouraud technique, which is more important for you to understand. So vertex shader Gouraud and fragment shader Gouraud. First the vertex shader. So in the vertex shader you just have anything you need in order to visualize the solid, and as color we just use the normal. But what we want to do is to move all the steps, the majority of steps performed in the vertex shader Phong inside the fragment shader Phong inside the vertex shader Gouraud, which is not as easy as it seems. So it's not that theoretically it's pretty easy. Implementing it can raise some mistakes, some error, but we try to do it. Okay, we want to move more or less everything we have here except the textures, because textures cannot be computed in a vertex shader. Here, in position and in normals are required, but we don't need an FS normal because everything is going to be computed exactly here, which is an approximation. We don't interpolate anything along the surface. We will see some difference in the illumination. What instead we need, so also this thing goes away, what instead we need are everything concerning the light. So specular color and specular power, not the diffuse color. The diffuse color, material diffuse color, is included inside the final color computation of a surface, and since we have texture, we have to pass that value still in the fragment. But those two are required. So spec color and spec power. Everything, again, concerning the lights, so direction, position, color, and type, must be put inside vertex shader. We also need the eye position and the FS UV, which we call in UV eye position and the UV. But we also need to send UVs for interpolation on the subsequent step. So those are the varying and the uniform that we need. Then we are going to send the next stage two more varying, which are, the first one is vector 4 with a partial color computation that we call Gouraud specular, and another one which is Gouraud diffuse. Those two we can copy and paste here. Okay. Now we have more or less all the parameters that we need. We are lucky enough that we can probably just copy and paste the function before the main, checking that we are using the same values. So light position and light direction doesn't have a name change, everything else is correct. Okay, so light model can be copied as it is. Now we can copy fs uv equal to, so in main this is the only interpolation that we perform, and then the GL position, which still is computed inside the vertex shader. Then we have to copy the rest, but checking that we are using the right values. So an eye direction is going to be eye position, but in position, and n normal requires in normals. Okay, then again we can call the light model, but now the light models use the in positions as a second parameters. The return values doesn't change. Then okay, diffuse color, we don't have a diffuse color texture mixture because everything concerning the texture cannot be used. We have a diffuse, so grab the diffuse part, but of course we don't have a diffuse color mixture, so the diffuse is going to be computed without the first value. L light color is the first of the terms that we multiply. LDIM and DIM. Okay. Reflection is going to be computed exactly the same way. Can be copied, and we can copy also the specular part. Okay. Reflection has everything correct. Spec color has everything correct. Instead of having diffuse and specular, we can use Gouraud diffuse, Gouraud diffuse and Gouraud specular to send values to the next stage. Instead of having computed things about and let's see what happened. Okay, perfect. You see that the highlights are basically very different, and probably with Spotlight you can see why the Gouraud method is called a sort of simplification. Since we don't have an interpolation along the surface, everything is computed only with the value at a vertex, and you can clearly see the geometry below. You can see the difference pretty clearly here. Okay. Something wrong with the textures. I was right. I will correct it. Okay. Probably I forgot. No, texture influence is here. Let's check it. Seems correct, but there is a mistake. Okay. Again, the final version will be correct, so don't want to spend too much time error checking. You will experience exactly the same thing. That's why I'm not spending time to correct that. I want just to show you the advanced texture used before. Okay, let's see this one, just to check if in the other, yeah, you see it will be exactly the same, so doesn't change too much. No, what I want to show you instead is okay, for example this one, which is an advanced use for text. Okay, let's go away. In this case, sorry. Okay, what we have here is exactly the same configuration we had before, but we are using the texture, a special texture, to create the illusion of having an horizon, which is more or less we have a cubic texture around our scene, which is projected to the infinity, basically. So it doesn't have really a distance. It will be always the farthest thing we have. But if you look at the texture from this example, you will see that models, yeah, this is a cube map, which is exactly what we have in the previous example, but in the previous example it was used as a simple texture, texturizing a cube, which have no special meaning. If instead we use a special algorithm or the cube map, which are implemented as a function, this cubic this projection of a cube can be used to provide the illusion of a background. You will see more about cube map in the theoretical part. I just show you the results so you know what we are talking about. You don't see, there are some problems given by the texture. In this case, you are able to see the lines. 1 pixel probably has been missed, and that's why you see the line down there. So that's one of the advanced use that you can have for a texture. It will create the illusion of a background, and you are not spending too many resources for doing that. Another advanced use is with, okay, this is just to show you ambient light. It's not particularly it's meaningful, but just to see, since inside the formula for light computation there is the ambient component for the light color, we try to see how ambient light influence everything. Let's see if we don't have ambient light. It's taking a while. There's some mistake going on. Okay. Just because the model was a little bit more complex and expressing everything in a textual file sometimes takes time. Okay. Okay, the model is from Harry Potter. It's Hogwarts destroyed at the end of the saga. Okay. So you can of course change everything, texturize everything. So you have an example of a very bad 3D object with just the textures and nothing more, which provides not that great results. Then we can, of course, increase the ambient, and that's what happens when we have an ambient light, in this case, for example, white, but we can change and put it to blue. So that's the general idea of how ambient light influences an environment, creating different lighting effect. You see also the zone outside the cone, since there is a diffuse component, an ambient arc can be seen, and that's the effect of ambient light, if you have it or not. We have another example, much more nicer effect. In this case, in this other example, instead, you have two different textures layered one over the other, which is a pretty cool light effect. Unity, for example, is able to compute this kind of illumination automatically. Basically what we have the same texture that paints the object, as here, but also we have saved over another texture some shadowing effect. Which are those? This is just plain ambient occlusion, meaning that the closer two objects, two surfaces are one to the other, the darker will be the color. So usually ambient occlusion by itself it's able to create realistic illumination effect. Don't consider the rooftop here, they have messed up normals probably, so something happened. Let's look at the good part of the model, and we can put them both together. Probably there you cannot appreciate the effect, you have to see all of this on your machine, but you will see something more realistic than the simple light, the texture, the use of texture. The last example is something completely different, another use for texture, which is used in many games today. You can store inside a texture the direction of the normals of an object. This procedure allows you to have a very low polygonal object, but with a normal map texture, all the details that are missing from the object itself are added using a texture, which is, as long as we decided to load everything. Okay, this is from Crysis 2, is the suite of the main character. We can show the normals, so you see that it's basically the same. Okay, let's do this. You see, this is the low poly model. It's just low polygonal and pretty jagged. If we apply the normals, we add basically details to the surface, only because the RGB values of the texture that you can see here now express a vector direction, not a color. That's the use commonly made of normal maps. So, since something about normal mapping or advanced texture use can be asked at your exam, I suggest you strongly to check the code of those examples and study it. It's pointless to implement it because it's pretty difficult, but if you grab the theory, you should be all right. Consider that all you have seen up to now is just let's say basic from mildly intermediate use of 3D computer graphics, because we have seen only one the pipeline, which is used just once. Usually you have more cycles in the rendering to add extra effect. If you have to compute, for instance, transparency, that is going to be a separate pass of the shaders. Here you have seen just one pass shaders, but shaders nowadays requires multiple passes for correct and advanced lighting effect. And another complication that we doesn't include was that of the animation, because animation includes a lot more matrices computation, and that also increase the complexity if you have to choose a different space for them. So consider yourself lucky. It's complicated, but it could have been much worse. Okay, so for today I think it's all.